and welcome to episode 2 of CS350 Online. I'm your host, as always, Leslie Eistedt, and in today's episode, we are going to start our discussion of threads. But first, just a few things I want to bring to your attention. We have the website mostly updated. I know it's still set to default to the winter of 2021. We'll get that switched, but if you just put the S21 at the end, you should get everything that you need for this term. The other thing I wanted to say is that for those of you who've tried to start assignment 0, that's now posted. The files are all there, along with all of the other assignments. And the reading assignments are going to follow very, very soon as well, so do pay attention, but they're not due for a while, so don't worry about those so much. So yeah, our course website's almost completely updated. Again, most of our communication is going to happen over Piazza, so make sure that you're paying attention to that every day. And the other thing I want to ask is that you search for your response or your question before you actually post it. That way we can minimize the number of duplicates. And I know a number of you are having a really hard time logging into the student environment. It's giving you this weird error messages about known hosts. You can either totally nuke your known hosts file. That's not actually necessary though. In the error message that you're seeing, you'll actually see an index. And all you have to do is nuke that entry that's prepended with that index, and you should be fine. Save the known hosts and restart. Now, for those of you who are trying to do this through VS Code, I am sorry I cannot offer you any assistance whatsoever. I don't use VS Code. I still use VI. Yes, maybe that makes me a bit old-fashioned. I'm not a big fan of IDEs, and I really hate it when it tries to guess what line of code I'm trying to write and tries to autocomplete it, and it's totally wrong 99% of the time. It's very irritating, so yeah, I don't do that. So I'm sorry I cannot help you with VS Code. If you are still struggling to get VS Code to connect to the servers, one of the things that I might recommend is if none of your classmates actually know how to do this, post on the Waterloo Reddit. I'm sure there's somebody out there that knows how to make that work. That's fine for this. The other thing I want to say is I know we don't actually get to see each other in person, and I'm sure many of you actually know each other outside of this virtual environment. But take a minute and introduce yourself on Piazza. Maybe there's a study group, and if you guys have, I see on Twitch that you've made a Discord server for help, please actually post that onto Piazza, because it would be really nice if everybody actually had access to that. We're not trying to stop you from helping each other. We just don't want you copying code from each other. So please, by all means, if you want to post any study group links or anything like that to Piazza, please do so. You're welcome to do that. There's also a few scripts out there for getting OS 161 working on your home computer or on the school servers. We are actually okay with you actually sharing those, so long as they don't include any assignment code, because I know it is getting increasingly difficult to actually get OS 161 running. For example, if you are trying to get OS 161 to compile and run on your home machine, it's going to be tricky. And one of the reasons why it's going to be super, super tricky is because the version of GCC has to be between 4.5 and 4.7. And if you do not have GCC between those two little numbers, it doesn't really compile properly. Now, some of them will compile properly, some of the aspects, but when it comes to compiling our specialized version of GDB, it will fail. Now, that being said, I have managed to get it running and compiling on, I have Big Sur now, but it doesn't work for everybody. So I will post the instructions and the patches that I made to make it compile with GCC 10. It's not fun, and it may not work for you because it really depends on how your computer's set up and so on and so forth. The instructions have also worked for some people on a Linux environment as well, but again, it doesn't work for everybody. So I will post that to Piazza. My recommendation for you, though, is if you can't get this compiling on your home machine within like a few hours of effort, stop and do it on the school servers where everything is already set up for you, essentially. And the reason for that is simply because you could dedicate a lot of time to trying to get things to compile on your home computer. We don't want that for you. We want you to focus on doing the assignment, not trying to get the code to even compile. That's not fun. Nobody wants to do that. I don't want to do it. I think I spent 2 or 3 days trying to get all the patches because I actually had to edit a lot of the files in GDB and GCC to actually get it to work, and that's not fun. Now, the other thing I wanted to mention is for a lot of you, I'm going to guess you're using a Mac, and I'm unfortunately using a Mac. But when you go into a terminal and you type GCC, you're like, oh, I'm using GCC. You're not, actually, and I'm going to prove it to you, because, I don't want to make it like some kind of baseless claim here. But if you type GCC into a Mac terminal, it obviously exists, but you notice here it says Clang. And if you type GCC -- version, you'll actually see that it is Clang, not GCC. And, oh, yes, you guys can't see the screen. Sorry. There you go. Now you can. So, as you can see, when you type GCC, it's Clang. It's not GCC on an Apple by default. If you want to have real GCC, and you need real GCC for these assignments, you actually have to manually install it, and you can use like Brew, or you can use anything like that to do it. And then what happens is when you want to use actual GCC, you'll have to actually type the version code as well. So on my computer, it's GCC 10. So there you go. See? GCC 10. And that one is actual GCC. See? Homebrew GCC. There we go. So make sure you do that. The other thing I want to say is you could probably hear some weird white noise going on. That's my fans on my laptop because, yeah, it's overheating. I have a new laptop picked out. Unfortunately, it's not released yet. So I'm sitting here waiting using this one here. And it likes to overheat doing this job. So we'll see. And if you're wondering, what magical laptop am I waiting for? I am waiting for the Asus Strix Scar 15.6 inch with the Ryzen 9 and the 32 gigs of RAM and the NVIDIA 3080. That's what I'm waiting for. And I know the 17 inch can be found, but I get so exhausted from carrying around 17 inch laptops. My last Asus gaming laptop was also a 17 inch, and I think in total it weighed 20 pounds with its power adapter. And I don't know. I don't really feel like carrying around something that big anymore. So I've got to wait for the 15 inch. Am I going to play Red Alert on it? Possibly. I honestly have to stop playing Red Alert because if I sit down and play it, I'm going to be playing it not for like an hour or two. It's more like 18 hours where you don't leave your chair. And I've got 2 kids, so that's not good. Although, admittedly, they'll sit down and play Zelda for 18 hours, so maybe that works. My 2-year-old's just gotten into Zelda too, so that's fun. All right, anyways. All right, so we're going to start each day then with actually a little bit of history. The reason why I wanted to do a little bit of history each day is because it's so easy in modern times to forget or not even know where we came from in terms of operating systems and computation. And I kind of really like computing history, and if any of you ever actually managed to make it to California, and it's not that you guys can't, it's just right now no one's actually allowed to travel, right? But if you do ever get to go to California, I cannot recommend enough going to the Computer History Museum in Mountain View, California. I know it costs money now. It used to be free, but it costs money now. But it is so worth it. It is so cool, the stuff that they have there. Maybe I'm just really nerdy, but I remember we got to play some asteroids on a PDP-1, and that was so cool because you're playing it on like a phosphor screen where it leaves behind like an echo of what was there for a good second or so. It's really cool. Anyways, it's a really fun place to go, but we're going to cover kind of a history of major operating systems, either in terms of because they did something interesting or because they were super important or because they epically failed. So we're going to do that for the first bit of each day. And I see everybody arguing on Twitch now about Zelda. Yes, my kids are playing Breath of the Wild. My 6-year-old daughter beat it 100% completion at Christmas. So now she's playing on Master Mode. And my 2-year-old son is, he's just learning how to throw bombs. And I'm not going to participate in the argument of 2D or 3D Zelda. I don't know what I prefer. Because I got to admit, there's some really good 2D ones too. Yes, 100% on Breath of the Wild is very hard for those commenting on that. That means you have to find all 900 Koroks. That's not fun. Anyways. This is OS, not Zelda. So the first operating system I want to talk about isn't actually the first operating system that ever came to be. It is one of the first commercial operating systems. And a lot of the operating systems have really bad names. So this one is GMNAAIO. So this was a product of both General Motors and the North American Aviation Association. And because this is 1956, this is running on a computer that is the size of the entire first floor of MC. This is actually a picture of an IBM 704 down here. And yes, it's black and white because this picture was obviously taken in the 50s. They did have color photos back then. They've had color photos actually for a really long time. But what you can actually see here is these funny little things that look like giant tape decks. Those are actually the tape drive storage. And then you've got an input system over here on the right, and then you've got some different computation banks and an operator terminal there. So this is a room-sized machine. And again, this was really early on. So all of this operating system really was a resident monitor, which is going to control what happens before and after each job, and a batch processor, which means that given a list of jobs, and they didn't really call them programs, I want to say they called them jobs back then, it's just going to run the jobs one after the other. So when one is done, the resident monitor will do some basic setup and then run the next one. And of course, the reason why there's the word I/O in the name of this operating system is because they offered a library of I/O routines so that you didn't have to worry about reading and writing these lovely, lovely tape units on your own, because that would not be fun. Fun story. So I don't know how many of you have ever actually used the Fortran programming languages. I have. You'll actually still see Fortran being used for the space agency and the military and in government applications. And one of the really interesting commands that you see, it's a legacy keyword, is rewind. And what rewind does it moves you back in the file. So if you're at position 5, rewind would move you to an earlier position in the file because it's rewinding where you are. But rewind traditionally actually meant not just move your position back in the file logically, but it actually meant physically rewind the tape. So that's kind of cool. So if you're wondering now, what kind of programs would have actually run on this operating system? Back in these days, the kinds of applications that you're looking at are not games. Games did exist, I want to say in the 60s. You'll start to see games come out. But what you're actually seeing here is things like inventory programs, payroll, keeping track of information like that. You're not seeing a lot of fun, applications yet. Also, no internet yet. All right. So that's today's OS, and now I would like to move on to our brand new topic. And, I so did not want to do that, Apple. So what we're going to start off by talking about is this concept of threads. And if you've never worked with threads before, this can be a little difficult to wrap your head around, which is why we actually have a assignment 1. And assignment 1 is actually very different from all of the other assignments because assignment 1 is not taking place inside of OS 161. What we are doing on assignment 1 is we are asking you to get some real world threading experience. We want you to use a library called pthreads or POSIX threads, which is a cross-platform, super popular library for doing multi-threaded applications. And we want you to solve just a couple really simple problems using pthreads. You've got starter code and all of that, and some basic rules to follow with it. And we'll post some links to help you get started with pthreads. We're not going to talk about pthreads in class. But that way, you know, when you actually go to apply to jobs, you can say, hey, I've actually done this in a real world environment, because the threading we do within OS 161, that's specific to OS 161. And so while you're learning theoretical concepts that are for threading, you're not really getting any practical real world experience. Hence why we've changed A1 to be something a little more real. Now, if you've done threading before, great. I'm sure this won't be that exciting for you. So what I want to do is I kind of want to talk about, before we talk about what is a thread, I want to talk about the concept of concurrency, and I want to talk about where this idea even came from. And it actually spans back to the OS we were just talking about. So once upon a time, computers could only do one task at a time. And that meant that you ran one job, and then when that job was done, you could run the next job. And that works, but here's the problem. Anytime you need to do an I/O operation, let's say you need to write some data to disk. Now, if we're writing data to a disk in our own machines, which most of us have SSDs now, that's really, really fast. And so our CPUs are going to be idle for a very small period of time. Well, in reality, our CPUs are never idle anymore. But back in the 50s, people noticed that because your disk drive was on the other side of the room, literally other side of this big room, traveling across a wire is not free. So it cost a lot of time to have the electrical signal travel from the CPU over to whichever disk tape drive you were using. And then once you get to the tape drive, it actually takes time for that tape drive to spin up, move the tape to the correct position, slowly acquire the data, because tape drives are not fast by any stretch. And well, back in the 50s they weren't anyways. Now they're a lot better. And then get the data and then send it back. So your CPU could be sitting idle, not for seconds. It might have been minutes. It could have even been more than that. And because there were so few of these computers back in the 1950s, and so much work people wanted to do on them, the thought of the CPU sitting there idle really bothered people. They're like, we're doing an I/O operation. The program can't actually continue execution until the I/O operation is completed. The I/O operation is going to be gone for a while. Why are we letting the CPU sitting idle? So they got with this idea of, is there a better way that we could do things? While the CPU is sitting idle, could we run another program? Could we improve the CPU utilization? And this is actually the beginning of where multi-threading and concurrency came from, is this thing called multi-programming. And the idea of multi-programming is when a program is idle because it is waiting for something, idle meaning it's not using the CPU, we let another program run. We are trying to maximize the CPU utilization by taking advantage of programs that are waiting. Now, of course, multi-programming, while it does improve CPU utilization, it doesn't necessarily improve the speed of the programs that are running. And the reason for that is because not every program is going to actually need to do these I/O operations. So it's not a perfect solution. And that's where this idea of concurrency and threading is kind of coming from, is how can we improve upon multi-programming to get it so that more programs are actually running at the same time? How can we further improve CPU utilization? But how can we actually, there's two other goals. How can we improve the performance of a program by letting multiple threads run at the same time? But how can we also give the user the illusion that all of the programs are running at the same time? So let's note, we're not going to talk about things in terms of jobs. We're going to talk about things in terms of threads. So what is a thread? First off, every program has at least one thread. If you do not have a thread, then you cannot run, because a thread is just a sequence of instructions. So everything that you wrote in CS136, everything you wrote in CS246 had at least one thread. Now, in 136, it was one thread only. 246 depends on how you did things. No, if you're wondering what magical thing am I drinking here, this is not wine, this is cranberry juice. All right, so what threads are for then? So every program has to have at least one thread or it can't actually execute instructions. Why then would you want to have multiple threads? Why have concurrency? Why have the ability to have multiple sequences of instructions executing at what appears to be the same time or is actually physically at the same time? Well, some of the reasons for doing that are improving your CPU utilization, improving the performance of the program, and another really interesting thing where sometimes we write multi-threaded programs is simply because there are different tasks that we might need to do, and there's no reason for them to all be happening in the same sequence of instructions. For example, if you're thinking about programming a video game, there's lots of very different tasks that are going on. You have the rendering task, whose job is just to render the screen right now, compute what the scene should be in this frame, and send it to your graphics card to render. Why should that thread also be doing the AI for the bots? Like, if you're playing Unreal, I don't want my thread who's responsible for rendering being the thread who's controlling the AI for the other guys. I'm not talking Unreal 3. I'm talking Unreal, the original one. One of my favorite games. So, we'd use multiple threads for a variety of reasons to express concurrency in a program. And what's interesting is the threads, they don't have to do the same thing, but they can. So you can have a bunch of threads doing the exact same task, or you can have a bunch of threads each doing different tasks. Now, if they're each doing different tasks, it might be due to, or this is a better way to organize our thoughts. And if they're all doing the same task, then often the reason why we have threads all doing the same task is because we're trying to improve performance of something. Now, there's lots of reasons more than just what I've already said about why we use threads. We've already talked about CPU utilization but we can expand upon that and just say resource utilization in general. Because there's lots of different resources that we may need to share. Parallelism. So if you only have one CPU with one core and it can only run one thread at a time, you're not going to be expressing parallelism because you don't actually have the ability to run two things physically at the same time. But I don't think any of us has a CPU like that anymore. And I haven't had a CPU like that since like 2000. 2000? I think the first hyper-threaded CPU I got was 2003. I think so. Yeah. So a long time ago. Everything that we use today has either multiple cores or supports some degree of hyper-threading. So, for example, this laptop that I have right now is an i9. It has 6 cores, and each core supports 2 threads. So that's 12 threads. So I am, with this hardware, actually able to express parallelism with threading, which is going to give us a significant boost to performance. Yes, I see you on Twitch there saying Intel EU. I know. The Ryzen 9s right now are beating the pants off Intel, but they're also practically impossible to get your hands on one right now, hence why I'm still waiting for my laptop to be released. I'm not going to comment on the M1. Now, some of the other reasons why we might represent a program with multiple threads is to get better responsiveness. And this comes down to separating tasks into separate threads. Because if you want your UI to be really responsive, then you don't want the thread that's handling the UI to also be the one handling your AI for your game. because it's not going to be able to be as responsive to mouse clicks and keyboard presses. And I don't know about you, but if I'm playing a game 60 frames per second minimum, or I'm throwing it out the window. Okay, that being said, when I was in undergrad, I would play Warcraft 3 at like 1 frame per second, and it was awful. Obviously, I bought a new computer, because you can't really play Warcraft 3 if you get 1 frame every second. It doesn't work. All right. So another thing reason why you might have threads is because not every thread has the same priority. If you think about all of the threads that are running on your computer right now, they're not all equal. For example, the thread you are using to watch this video stream, whether it's live on Twitch or whether you're watching it on YouTube later, well, that thread is a higher priority thread because it's going to be requesting data and then wanting to show that data to you. So we want that thread to be very responsive for when network packets arrive. So we want to make it a higher priority than maybe you've got BitTorrent running in the background. Now again, BitTorrent is something where packets are arriving and it doesn't want to receive them, but it's not something you are actively paying attention to. I mean, if you're sitting there watching BitTorrent and watching the bits arrive, you need a new hobby. Seriously, go outside. It's a nice day out today. And then we have, again, as I've already mentioned, modularization, just a nice separation of tasks. Now, a question on Twitch is, what is your opinion on the M1 from a CPU perspective? I haven't done a lot of research or reading about the M1. To be honest, I'm kind of skeptical. I don't know how much about Apple's history you guys actually know, but Apple actually used to have non-Intel based CPUs. They actually used to use PowerPC up until I think they released Mac OS X. And then sometime around Mac OS X, they switched over to Intel. And during the days where they were using PowerPC, I want to say that was a real low point for Apple. And I'm not saying the M1 is in the same boat, because I don't really know much about it. I have a lot of skepticism about it. And that's healthy because we don't have a lot of information and experience with this chip yet. It hasn't been out for decades. Whereas if you look at AMD or Intel's hardware, even though their chips are new, they've been around for a really, really long time. So we know a lot more about their general behavior. Whereas the M1 is new and we don't know a lot about it. So yeah. I don't really have an opinion on the M1. I have a lot of skepticism, but it's not something I'm going to find out because I'm not buying an Apple laptop. All right. Now, I've said that you could use threads in a couple interesting ways. One of the things I said is that you could use threads to improve performance, and you can also use threads to give the illusion of multiple programs running at the same time. And what I would like to actually do is show this to you. So, I am gotta get into the right directory here. I have 2 little snippets of code, and they're the same, except for one tiny bit. Yes, I know this is written in C++ and not C, and this course is a C programming course. I have a strong preference to use C++ over C. And admittedly, when I say C++, I'm probably saying C++ 99. All right, anyways. So what I've got is a little snippet of code, and I work in computer graphics, so I do a lot of stuff with image processing. So I've got here an image that is a 4K size, so 4096 by 2160 is a pretty standard 4K resolution. And I have this little function here where after I set up an image, I want to swap the colors. So in swap colors, it plays around. It does some operation to each pixel in the image. This code here does not use any extra threads. It is a single threaded program, which means that we are going to process each pixel serially. So That's not that exciting. This is the kind of code we're used to writing. But here's the interesting thing. If I am processing each pixel separately, then each pixel could technically be handled independently. And if each pixel could be handled independently, then that is a key thing that you could be parallelizing through multi-threaded code. So, what is a long? I don't remember how many bits it is, but it's a lot more bits. Why am I using a long? I don't know. I think I had bigger numbers in there, but then I got really impatient about waiting. So if I look at the same piece of code, and this time I'm actually going to use threads. And I know I have not talked about this particular threading library, and this is not pthreads. This is one called OpenMP. I call it lazy threading because all you do is put in a bunch of preprocessor directives and magic, you get threads. You don't really have to do much work. So what I've done here is I've asked OpenMP to automatically parallelize this loop for me. And it will add enough threads to parallelize this loop. So it's the same code as before, except now each pixel in my image, instead of being processed serially, they're not going to be processed in parallel. Now, is it going to be like all millions or in parallel at once? No, we're going to it creates a reasonable amount of threads and then processes just many of them at a time. So let's actually look at a comparison between running the no threads version versus running threads. So I've already compiled these. So we're going to time them. Now, time is a command. It doesn't matter whether you're on a Mac system or a Unix-based system. That's a command you're going to have. And so let's run no threads with time. And of course, my CPU is being throttled down because of all the stuff I'm running. So you can see here, now what you've got 3 different times. The one we care about is real. That is how much time it elapsed according to you, the human sitting at the computer. And you can see here it took over 3.5 seconds. Now I can do the same thing with my threaded version. And wow, look at the big difference here. I went from over 3.5 seconds to just over 1 second. Now, when I ran this earlier, it actually ran a lot faster, but I also wasn't, streaming 4K video at the same time. So, and now one of the things you're going to be really confused about here in these numbers is you're like, oh yeah, I see the user time here is less than the real time, but wait a minute, this only took 1 second. Why does the user time say 4.6? That's because it's computing, it's the sum of how much time it took across all the CPUs, all the cores it ran on. So that's what you're seeing there. So as you can see, when you have the ability to multi-thread something, so long as your CPU actually supports threads running in parallel, you can get significantly better performance. Now, the threading library that I just used is called OpenMP. I'm going to jump ahead in the slides here because we do talk about it. I got to make sure I'm scrolling in the right direction. So OpenMP is a cross-platform API for doing multiple threads. It is really, really easy to use. Are these code examples posted? They are not, but I can post them for you if you'd like. I use OpenMP because it's really simple. And if you're not looking to do any complicated multi-threading, I find OpenMP is usually the fastest way to do it. And you can do more complicated things with OpenMP, like synchronization. You can specify exactly how many threads you want and things like that. So it is much more flexible than what I've shown you. But if you want to do threads like that, it's really easy. Other thread libraries that exist are pthreads, POSIX threads, and you're going to be using this on assignment 1. And then if you really want to take your multi-threading to the max, you can do GPU programming, which stands for General Purpose GPU Programming. That means instead of writing this to run on my CPU, I could write it on my GPU. And you'd be like, why would I want to do that? Well, because your graphics card has way more cores than your CPU. And by way more, I mean like thousands. And if you're sitting there wondering, well, if my GPU has thousands of more cores, why don't I use it for a CPU? Because it's missing a lot of things. There's a lot of assumptions that graphics cards make that work for graphics cards but wouldn't work in general. For example, on most GPUs, they only have one program counter. So all cores actually have to be executing like the same instruction at the same time. And if you have any branching, the GPU actually has to stop executing in parallel and start executing in serial because it can't have two different ones. Now, I don't know if they're changing that architecture at all. That's going to be more costly. It's going to slow things down. But yeah, GPUs, if you write the code correctly, can give you hundreds of times improvement in terms of parallelism. Now, another question on Twitch is, if you ran the threaded code on a single thread CPU, would it be slower than the non-threaded version? Yes, that's actually entirely possible. And the reason for that is because, sorry, falling into my chair here. So we were able to get some better performance out of multi-threading because our CPU actually supported that in hardware. But that's not, if you can't support it in hardware, then those threads all have to share the one CPU. Which means what we're going to do is in order to share, we rapidly switch between them. So that's going to add some cost. And then the threads they're all going to make progress, but at a little bit slower rate. So it's not, you can improve performance of some tasks, especially if there's I/O operations. But we didn't have any I/O operations in that code, so it wouldn't actually, on a single-threaded CPU, that wouldn't give us any performance boost. Now, if our code, our multi-threaded code for a single-thread CPU did have I/O ops, then we would get a bit better performance because we'd be improving our CPU utilization. But we didn't have any I/O ops, so it would run slower on a single-thread CPU. So that's threading in the real world. Now I want to go back and talk about threading in OS 161. So what I'm actually going to do here is, I am on the wrong screen thing. There we go. Now you can see it all nice and big. I always forget to change my scene. All right, so I'm going to open up a terminal here, and we're going to actually look at some code for OS 161. So first off, let's switch to Bash because no one wants to use ZSH. And I don't care if that's the default. So I'm going to go, first off, where I am right now is in OS 161 kern directory. All of the development you're going to be doing this term for OS 161 happens in this directory. So we are actually going to go into test. And inside of test, I am going to open up threadtest.c. And then the line number I want to go to is, I forgot to write it down. So I guess I have to find it the manual way. So we are going to go to loud thread. So loud thread is the sequence of instructions that I want each of my threads to execute. And what it does is it's going to print a number onto the screen, its thread number, 120 times. That's why it's called loud thread. And then in OS 161, in order to create a thread, we use this function called thread fork. And it takes 5 parameters, 5 arguments, and I'll go over what those are in a minute. So what I'm going to do in this particular little piece of OS 161 code is I am going to create 8 threads. They're all going to run loud thread, and each of those 8 threads should print their number 120 times. Now the interesting question is, how does that look? When I run this test, what's actually going to be printed onto the screen? So this is the thread library for OS 161. Now let's actually test this program. So for those of you who have not yet got this running, to run OS 161, you need to run it in a simulator, which is sys161. And then you have to specify which kernel you want. I'm going to use the assignment 0 kernel, which I actually don't think I've implemented any of. And, give me no CPUs and give me no lives. That's hilarious. That is the best kernel panic ever. Okay. Sorry, I'm trying to go to the bottom of this file because I set my CPUs to 0. That's really funny. Okay, there we go. I have to have at least one CPU or it won't do anything. So now we've booted up the operating system. And if you push question mark, it'll tell you the different menus that you have. And we want to look at the tests menu here. So question mark T, this is our tests menu. Now, a lot of your tests actually come through this menu here. So the allowed thread test is thread test 1, so TT1. So if I type TT1, we're going to be running loud thread. Now, what could our output be? If you've never worked with multi-threaded code before, it's very easy to believe that because we created the threads in sequential order, thread 0, then thread 1, then thread 2, that we'll get 120 zeros followed by 120 ones, followed by 122s, and so on and so forth. But if we actually run the test, that's not actually what we get. So it starts out 0, 1, 2, 3, 4, 5, 6, 7. And then it repeats. Now, what's really interesting about this is that that sequence actually breaks pretty quickly. So we get 1, 2, 3, and in the fourth sequence, we see that thread 7 didn't actually sound off. And if you look at the very bottom, we have 70345703. What's going on here? In order to share this one CPU, these threads are rapidly switching between each other. So they are only given a short period of time to execute before we force them to give the CPU up to somebody else. We want to make it look like all threads are making progress at the same time to the user. Now, why didn't it maintain the pattern? Because sometimes, number one, we're doing I/O operations, we're printing to the screen. And sometimes that takes longer and sometimes that takes less time, which means that the next time we go to get a thread from the pool of all that are ready, that thread that should logically go next may not be ready technically. So we have to pick a different one. And over time, you get a weird sequence. Now, what's really interesting is that pattern of 120 zeros followed by 120 ones and so on. That is actually entirely possible. And in fact, every time I run this test, I'm going to get a completely different result. I can even get the same number back to back. That's totally plausible. So when you're running multi-threaded code, one of the things I want to remind you of, number one, you have no control over what order the threads actually execute in. No control. That has some pretty bad side effects. We'll fix them in the next section. The other thing to keep in mind is that when you have multiple threads, it can be tricky because you have no control to predict what the behavior is going to be. There's multiple different ways the program is going to execute now. So there can be lots of interesting different outputs. All right, to leave OS 161, you're going to hit Q and that will drop you right out of it. No, I did not mean to open that up. Oh well. So the OS 161 threading library consists of just 3 API functions. We have fork, which as I said takes 5 arguments. The first argument is the thread name. Now you might be thinking that the thread name is how we uniquely identify threads. It's absolutely not. There's no restriction or checks to make sure that the names of threads are unique. This is more for debugging purposes. The unique identity of a thread is the address of the thread structure. Because if we actually look at what is a thread in the operating system, we'll do that right now. What is a thread in the operating system? Let's go into the include directory and let's open thread.h. And if you go to line 68, a thread in the operating system's kernel is a structure, and it contains the name of the thread, a wait channel, which is something we'll talk about another day. It contains the thread state, i.e. is it asleep, Is it ready? Is it running? It also contains information about its stack, and we'll talk about that in a few minutes, what CPU it's running on and what program it belongs to. It also contains things like a pointer to the instruction we're currently executing. So inside of your kernel, a thread is just a structure. So we have thread fork to create a thread. So we've got the name, the process, which is which process do you belong to, and all of the threads that we're using right now actually belong to the kernel. So we set the process to null. Then we have this. It's a function pointer. And I want you to pay special attention to the signature of this function pointer, because when you use thread fork, if your function does not have this exact signature, it's not going to compile. The function pointer is a pointer to the sequence of instructions we want this thread to execute. Okay? And then we have two pieces of data that we can pass along to the thread so that it can run its function. So that creates a new thread. It actually creates a physical new thread structure for the given process, and then moves the thread into the ready pool, which again, we'll talk about in a bit. Then we have thread exit. Now you don't explicitly need thread exit because a sequence of instructions for a thread is a function pointer, and when you reach the return of that function, it will terminate the thread. But let's suppose you've got some deep recursion and you don't want to pop it all off and you just want to kill the thread like that. Well, then you can call thread exit and just immediately terminate. And then we have this function called thread yield, and this is a really fun one. This is a function that lets you voluntarily give up the CPU. Now you might be like, why would I do that? There are reasons to do that when it comes to synchronization. Let's say we are waiting for something to change and our thread has to wait until it is changed. Then we might want to give up the CPU to improve the chances that the variable we're waiting on changes. And we'll talk more about that another time. Now, a question on Twitch is, how is multi-threaded code tested? Yeah, that's kind of a nightmare, actually. So for this course, the way that we recommend you test your multi-threaded and multi-process code is through statistical testing. That is, you're going to need to run the tests hundreds of times. So write a script to do it, capture the results, and then sift through the results or write another script to look for failures. The reason why it's really hard to test multi-threaded code is because you have no control over the order of execution of the threads. And one of the really bizarre things you're going to see with debugging and testing multi-threaded code is that you run the code, you get the wrong output. So you put in some printfs thinking you're going to find where it went wrong, and the code runs perfectly. And you sit there scratching your head. And the reason is by putting those printfs in there, you change the order of execution, and now you don't have this problem. This problem, by the way, would be called a race condition, and we'll talk about it in a few episodes. So here's the thing. It's hard to test multi-threaded code. And if you're thinking that every piece of multi-threaded code out there in the world in production and for sale works perfectly, you're absolutely wrong. Google did some analysis of the Linux kernel a couple of years back, and they found over 300 issues. And I think they were a combination of race conditions and deadlocks. And I'm sure it's not just the Linux kernel that fell into that boat. I promise you that Windows has, the same things, and I promise you macOS also has similar issues. It's just their code's not open, so we can't test it, right? So it is very, very, very difficult for you to test multi-threaded code and know that it's always going to behave exactly the way you want when you want. A lot of times we have to look at things on paper and try to figure out, okay, if I analyze this code theoretically, am I doing things the way I want? Is there any way that some order of execution causes this to behave badly? So 2 other questions on Twitch here, several questions. Do you need to dig out your bash notes from 246? Yes. Stack Overflow is pretty handy too. You don't need to submit your test scripts. So if you want to Stack Overflow that, you go right ahead. And in fact, if one of you makes an environment to test things and you want to share that, as long as you're not sharing OS161's code, that's totally fine by me. Yes, race conditions are fun. Fun. A0 is going to walk you through... I mean, in order to get A0 running, you have to actually get the environment set up, and you have to go through all the guides online to get that working. And then A0 is a very brief introduction of code. Put your name on it and add a menu option. So it's just kind of a taste of OS 161, but you're not really doing a lot of work with it. And then the last question is, do real-time operating systems have the same issues? Absolutely, because they have multi-threads too. And they have the added constraint that threads have to be guaranteed to respond to events in a specific amount of time. So it's even, their requirements are even more stringent. Okay. Now, some of you who have done threading before might have noticed that OS 161's threading API is missing a function called join. Yeah, we don't have join. It's not that we don't have the ability to do this. So what join is it forces a thread to wait until another thread has completed. We have the ability to do that in OS 161, but not via the threads API. You can do that with things like locks and condition variables and semaphores, which we'll talk about in synchronization, because those are the things we're going to use to stop the race conditions. But we don't have an explicit join function. Now, you will find join in things like pthreads, but for assignment 1, you are not allowed to use join in any way. We'll clarify that a bit more on Piazza when the time comes. Now, if you're wondering, how long have we had this modern concept of threads for? That's really new, right? Totally not. Our modern idea of multi-threading and concurrency actually originates in the 60s. So it's been around for a really long time. And a really, really interesting story, Windows and Mac OS haven't really used this modern idea of concurrency until the 2000s. And we'll talk about that when we talk about some of these things in a bit greater detail. All right. Now, I want to kind of end today's episode with a bit of a review. So first off, sequential program execution. So remember CS351 and CS241. I know they were a really long time ago. And I know that the second you write an exam, poof, the course is gone from your head. So if we have just a regular single-threaded program, you know that your CPU has a number of registers. And remember, we are using a MIPS CPU. Now, for the people who are on Twitch, did you guys in 251 do ARM or MIPS? I'll just give you a second to answer that question. ARM, okay. So just for those of you, because then if you haven't used MIPS before, MIPS and ARM are actually in the same family. They are both RISC processors. That means they are reduced instruction sets. And they're very similar. I want to say even their instructions are similar. There's a lot of similarities between them. So our CPU has a number of registers. Among them, we have a program counter, which is going to contain the address of the instruction we're going to execute next. We also have a stack pointer, which points to the top of the stack. And then our CPU, and it doesn't matter which one you have, was that the fetch execute cycle. We fetch the instruction that the program counter points to, we decode that instruction, we execute the instruction, and we increment the program counter. And this actually repeats on your computer until you shut it off. It doesn't know how to really do anything else, especially this MIPS processor we're using, which is pretty basic. Now, for the record, for those of you who don't remember MIPS that well, you are not going to be writing any MIPS assembly code for this course. There's a few instructions that we would ask that you know what they do, and we'll be introducing them in the synchronization section, but there's no assembly code for you to write at all. You don't have to interact with assembly code in any way, shape, or form on the assignments. The other thing I want to say is that, so we are using MIPS, and that means we have the 32 registers. Now, a couple things. The particular CPU we are using is called the MIPS R3000, and for those of you that are sitting there, like, why do we keep using these MIPS things? They're not real. MIPS is absolutely a real thing. This is not a made-up education CPU. MIPS is real. And in fact, a lot of my co-op jobs were actually writing code and compilers actually for MIPS CPUs. So the MIPS R3000 that we're using is actually a real CPU. And you want to know where you've seen it? How many of you owned a PlayStation 1? Because if you owned a PlayStation 1, guess what? It was a MIPS R3000. It's a real thing. And if you had a PlayStation 2, one of the coprocessors was an R3000 as well. MIPS was actually massively popular. Was it used for PCs? I want to say the SGI machines used MIPS. I think, if memory serves me. I gotta think about that. It hasn't been used for PCs in a long, long time. MIPS isn't as popular anymore as it was through the 90s and the early 2000s because ARM's really taken over. But MIPS was exceptionally popular, and I know I've written compilers for vector-based MIPS processors, and that's a really cool kind of MIPS processor. It's each register, instead of being a single value, is actually a vector of 8 values. So you get some really cool things you can do with that. So I'm just gonna quickly Google this here. Yes, so people were asking, was MIPS actually being used in PCs? So as I thought, it is SGI, which is Silicon Graphics, which doesn't exist anymore. But Silicon Graphics did use MIPS processors in their hardware. Actually, Silicon Graphics bought MIPS many, many years ago. But SGI is dead. And there you go. I think SGI, when I was down in California in 2007, I think SGI sold for $25 million. And I was sitting there, man, I could own SGI if only I had $25 million. If you're not a graphics person, SGI probably wouldn't mean much to you. But it's a company that used to make boxes specifically for graphics applications. So just to review then of our registers, we have 32 of them, but inside OS 161 we do not refer to them by their number. They have been named. And the name here is sitting there. We have actually also, as part of the operating system, designated certain registers to have certain purposes. So 0 is always going to be 0. That's just a part of MIPS. 31 is going to be RA, the return address, 29, the stack pointer, and so on and so forth. Now we have some special ones. We have one is assembler reserved. We have 26 and 27 are kernel registers that we're not going to touch. The general purpose registers that we are allowed to use in our programs are the S's and the T's. So these are the registers between 8 and 15, 16 and 23, and 24 and 25. And those are the general purpose registers that programs can use. Now this is an interesting thing because you might be like, well, what if I just want to write an assembly program and run it on through OS 161. If you do not obey these conventions, your program won't run properly because the operating system and the compiler have agreed to use these registers in these specific ways. So if you write a program and you don't use the registers in these ways, it won't work properly. And this might bring you into discussion. Wait a minute, the compiler and the OS have to agree on things? Yes. Yes, they do, because the compiler has to know how to compile the code for the OS, and the OS has to tell the compiler what it's expecting. So when you develop an operating system, you need to make sure that you're also developing the compiler that can compile the program specifically for that OS. So these conventions are set and agreed upon by the OS and the compiler. Now, we also have 2 return value registers, V0 and V1, and we'll talk about them another day. And we have A0 through A3, which we use for arguments to functions. And if you have more than 4 arguments, we put them on the stack and we pass the address, standard stuff there. So then, what are these temp registers? You'll note they're actually divided into 2 separate groups. There's the caller save and the callee save. As you know, when you make function calls, if you want the registers to be usable in the function that you've called, You have to save them before you use them and then restore them. So the operating system, the compiler, in order to reduce the number of things that you have to save, in general, they've agreed to this convention where the caller save register, or the T registers, are going to be saved by the calling function. And then the callee, before use, and then the callee save registers, the S registers, before the called function may use them, they are responsible for saving them. So we have this convention to indicate who is responsible for saving and restoring what prior to use. That way, the called function can use the T registers freely without saving or restoring, and the callee function and the called function can use the other ones. So if we look at this really quickly, and again, this stack is kind of written upside down from how I would normally do this, but if you have function A calls function B and function B calls function C, you'll see them on the stack like this, and then A is the caller and B is the callee, and then in this case, B is the caller and C is the callee. So that can get a little tricky. Now, how does this work when you've got multiple threads? So what we've got here is this picture of the address space, and here's some really interesting things. Threads of the same program share the address space with each other. That means that all threads to, let's say, Red Alert 2, which I don't actually think is a multi-threaded program, not the original one anyways. There's a remake, which might be. Anyways, so actually I have the code to Red Alert 2. I should go look at that. I'm not sure where I put it, but I'm pretty sure I have the code to the original Red Alert 2, and I should really take a look. Anyways, all the threads of a program are sharing the same address space. There's not one copy of the code for each thread. All the threads of a program actually share the same code segment. All the threads of a program also share all the global variables and the heap. So you don't get a separate code, heap, and global section for each thread. All the threads are sharing those things. And then stacks, instead of having one shared stack for all the threads, each thread gets its own stack. It's not, I mean, you could have the threads share a stack, but that would be a nightmare in terms of management, wasted space, not being able to pop things off correctly. So it's much easier to give each thread its own stack. Now, I know some of you are going to ask, but doesn't that mean the stacks are going to run into each other as they grow? Well, here's an interesting thing you may not know about stacks. They have a fixed size. And that's not, a MIPS thing. That's not an ARM thing. That's a real world thing. Your stack in Linux and macOS and Windows has a maximum size. And it's usually between 1 and 2 megs, actually. And if you don't believe me, go create a really large object on your stack. So make a structure that contains two giant 2D arrays, and then make an array of those structures on the stack. Yeah, you'll run out of stack space. There do tend to be functions that would allow you to change the stack size of a program, but they do technically have a maximum size. In OS 161, it's 4 kilobytes, by the way. And yes, somebody says stack overflow. Yes, and you may have actually encountered that in CS135 because there's a limited stack size. And if you have infinite recursion, you're pushing all those things onto the stack, and eventually you run out of space. So you get a stack overflow. So, question is, does the stack just offload the extra data to memory? No, actually, when you run out of stack space, your program dies. So it's an error if you run out of stack space, and your program will actually terminate and die. And that's a desired behavior. Now, some programs will say, hey, do you want to expand your stack space? And they might let you do that through a system call. But really, it depends on what does your OS support. Does it support changing the stack size? And things like that. So it's there you go. All right, now in this picture also, so each thread has its own stack. We've also kind of made you believe that the CPU has a set of registers for each of the threads, and that's absolutely not the case. A CPU only has one set of registers, but the idea is whichever thread is running, their values will be stored in the registers, and then the threads that are waiting to run, their copies of register values will be stored on their stack. Now, if we have a multi-core CPU, there's often a set of registers for each core, and in which case, you can actually have two threads, and if they're actually running on separate cores, it may actually have their register values stored in the real registers. So it really depends on how that works. All right. So this is, I think, where I want to end things today, is to just talking about the different ways that we can implement concurrent threads. And sorry, I'm just looking at this Twitch here. I'm not sure what that icon is. It looks like a weird hexagonal thing. Anyways, so there's different ways that we can implement concurrency on your PC. We've kind of talked about these different ways. The easiest way is hardware support. So you want to have multiple threads. You want to express concurrency. You want to have multi-threaded programs. Then you need hardware support for that. And these days, every PC has hardware support for multiple threads. Depending on what kind of processor you have, you may have something between 2 and upwards cores. I know my research computer, which is currently down because the motherboard's coding out and I got to get that replaced. It has 32 cores. And so I can actually, we can run a minimum of 32 as actually 64 threads in parallel. Okay. So what is the difference between processes and cores? So let me bring up a little picture for you. So a processor is the actual physical chip. But if you actually look at the silicon, this is really cool. Let's see if I can find an i7 silicon. Just looking for a picture here. I know I'm sharing my screen with you and you're like, wait a minute, she's looking up something, but I can't see what she's looking up. It's because beside the screen I'm sharing is my regular Apple screen, and then beside it, attached to the same computer, is a 38-inch ultra-wide, which you can't see. So what I've got here, I got an i9, so that's super awesome. So here we go. I'm going to bring that over. Sorry, my two screens have a very different resolution, so it's a little bit weird to bring this over. There we go. Okay, so this is a picture of an i9 chip. Now, what you might notice about it is it looks like a bunch of things have been copied and pasted. So this whole chip is the processor. And then on this processor are a number of cores. And the cores are these repeating blocks. So you can think of it as it's as if we've taken a bunch of smaller CPUs and copied and pasted them onto a piece of silicon and called that whole thing a chip. So yeah, a processor is the physical chip itself, and then the cores are how many processing units on that are actually in there. That's how I would kind of describe it. I think it's pretty neat. So if we're supporting threads with hardware, then what we actually have is for each processor, and your computer, by the way, can have more than one. In the 90s, it was kind of common for high-end machines to have two processors. Supermicro used to make motherboards that supported two processors, and I know my friends always got a Supermicro board. I didn't have that kind of money. Yes, so question is, so cores plus stuff equals a processor. So the processor is the chip. Sorry, I don't actually have a chip lying around my house anymore, but it's the actual chip itself that you put on the motherboard. And then if you were to actually look at the silicon, you'd actually see that there's this repeating computation block, and each of those computation blocks is a core. And you can kind of think of it in itself as a processor. It's just they've all been put on the same board, the same chip. That's a really simplified description of what's going on there. The cores actually share a lot of things, which is kind of interesting. So our hardware support, our computer has some number of processors, so physical chips. Each of those processors has some number of cores, and each of those cores supports some degree of multi-threading. So for example, Intel's hyper-threading supports 2 threads. So the total number of threads you can run simultaneously, that is in parallel, is the multiplication of those 3 values. So P times C times M, which is why my Core i9 here, I say can run 12 things, because my one CPU has 6 cores, and each of those cores has a degree of multi-threading equal to 2, so 12 threads. Whereas my Threadripper, which is in my basement, so it stays cool, has 32 cores and can run 64 threads. And yes, I see the comment on Twitch. Usually we just see the heat spreader with the CPU now. Yes, because you have this little tiny chip, and then I have a water cooler downstairs with a great big heat sink on top of them. But when I dealt with 486s, the heat sink was almost nothing. It was almost non-existent because they didn't really generate any heat. They also didn't go very fast. So question is it better to run on 2 different cores than on 1 core but multiple threads? 2 different cores, actually, is much better than running 2 threads on 1 core. And that's because usually of how hyperthreading's implementation work. Now, I haven't read a hyperthreading paper in probably 15 years, but I would definitely run it on 2 separate cores. Because hyperthreading, I think, to some degree, is not technically running in parallel. But again, I haven't read a hyperthreaded paper in over 15 years, so they may have changed that. So what if you want more than 12 threads? Because, if you look at your computer right now, let's look at this. I'm going to open up top. I have 2,200 and some number of threads. Okay, then. How is that working then exactly? Because I only have, my degree of hardware support is only 12. So how am I running 2,000 different things? Well, it's called time sharing. So effectively, we are rapidly switching between threads that are running. It's kind of like a physical timeshare. Like you can't afford a vacation house in Mexico, so you get together with 19 of your friends and you pool your resources together to buy one, but now you only get 1/20th of the time at that vacation house. Well, the same thing is true for timesharing. We have a physical number of resources where we can actually physically run the threads, and all the threads are going to have to divide their time across those resources. So we've got to do fair sharing. Now, in reality, because we have hardware support, we are doing a combination of both of those things. And in this course, we're not going to talk about hardware support because it's boring. Time sharing is the interesting thing, and that's where we're going to focus our time. So another question on Twitch is how cores support threads physically. So again, this is really architecturally specific, but one of the ways that you could do it is you could have each core actually be registered as a separate CPU. And in fact, if you open up the Windows Task Manager, you can actually see each of them separately, usually. I mean, you used to be able to. I don't use Windows that often. And then what happens is, so each of the cores probably has its own set of registers, and so each of the cores, when we talk about scheduling, will also have its own scheduler. So as threads need to be switched, we will put them onto a core that has the lowest load or something like that. And again, we'll talk more about that in scheduling. But yes, it's architecture specific, but also how does the OS actually handle it, and we'll talk more about that in scheduling. Okay, so I'd like to leave things here for today, and in our next episode, so that's Tuesday of next week, we're going to do a deep dive on how time sharing actually is implemented. So how does this actually work? How do we force a thread to give up a CPU when it doesn't want to? And how do we save the thread such that when it gets to run again, it actually gets to continue from exactly the point where it left off, as if nothing would happen? We don't want the threads to be aware this is happening. So we're going to continue that discussion in our next episode. And I think in our next episode, hopefully we'll have some time. And what I would actually like to do is walk you through how to use GDB for OS 161. Because I hate to tell you this, printfs don't really work. They're useful for kind of narrowing down where the bug might be. But at the end of the day, GDB is really going to be your friend for debugging in this course. And if you don't know GDB, please look at the tutorials on the course website. Because you got to learn to use it for this. All right, so we will see you on Tuesday. And for those of you who were wondering last time, was I playing the game live? I wasn't. So it was me playing the game, but unfortunately, DOSBox doesn't really work properly in macOS. So I played it the night before, and then I recorded it. If I get that fixed, I will play games live, but we'll see what happens. All right. And the question about the access code. Oh, yes. So I will post the sample code to Piazza under that extra sample problem thread, okay? And then all of the other code you saw from OS 161, you already have it. It's all included with OS 161. All right, so we'll see you on Tuesday.